So we're looking for equivariant version here. And so I'm going to need to tell you what are the analogs of sort of some of the key players here. So instead of having a ring, I'm going to have a Tambara functor. I'm going to jump right to the commuter case. So R underlined is the Cn Tambara functor. That's going to take the place of my ring A. And then instead of THH of my ring A, what I'm going to want is what's called Cn twisted THH. THH of Cn of, well, either I could write R, my Tambara functor, or I could write HR, the Heisenberg plane spectrum. As is usual, when I'm picking THH of a ring, I really mean THH of a ring. Okay. And this is a construction due to Engelfeit, Lumberg, Gerhardt, Lawson, and Mandel. And here and after these folks all together will be called A, B, C, H, M, because a lot to write. And so this is the spectrum that we're going to be interested in, is this twisted THH of our Tambara functor R. And what's going to play the analog of the Witt vectors for us is the version of equivariant Witt vectors due to a subset of the same folks. So the Witt vectors, the p-typical Witt vectors of length k plus 1, will be replaced by equivariant Witt vectors, which are denoted like this. So they're like the Cp to the Kn Witt vectors of R. Equivariant Witt vectors. And I'll tell you a bit about these, but just to get a sense. And these are due to Lumberg, Gerhardt, Lawson, and when I write HHL, that's the collection of authors I have here. So I'll have to refer to both of these pieces of work a couple of different times. Okay. And so then let me tell you the analogous result to this one of Hesselhoff and Max, and this is due to me and my collaborators, so Tina Gerhardt, Cameron Kalinowski, Sarah Peterson, and Lucy. So, again, we work at an odd time. And let's now need N. So N is going to be the order of the cyclic group that acts on everything. We have equivariance with respect to a cyclic group. And so N should be coprime to P, one of the requirements. And then R is the Cn functor. And we have the analog of this requirement that everything be z-localized at P algebra is going to be that I have a z-localized at P algebra at every level of my Tambara functor. So such that are evaluated at Cn mod H in z localized P algebra H inside N. Okay. So then collection of green functors given by the green functor homotopy groups to the group Cp to the Kn, THH, twisted THH, R. This collection is K runs over all the common integers, this is an THH Equivariant Witt complex over our base temporal function. Okay. And this, what does it mean to be a THH equivariant Witt complex over something? Well, this is going to be an algebraic structure. If you're familiar with the non-equivariant Witt complexes, you'll see some parallels, and I'll point out some parallels as well as we go along. So, many of the pieces in this theorem are probably unfamiliar to most of the people in this room, but the rest of the talk is going to be devoted to unpacking them and giving you a little bit of sense of what's going on. Before I start actually sort of getting into those ingredients, so I want to say sort of like two main ideas that I find helpful to keep in mind in thinking about this whole picture. So one is that for those of you familiar with the classical Witt vectors, you'll know that understanding them sort of as a ring and their multiplicative properties is like kind of messy. The definition of the Witt vectors as a ring is like a little bit head scratching. And one of the things that goes into the equivariant Witt vectors and Witt complexes that I like is that a lot of the multiplicative properties that we need end up getting taken care of by equivariant norm maps. And for me, this is an observation I think due to Morgan Broom in some sense many years ago. But for me, the fact that I've got norm maps coming up makes me feel much happier about Witt vectors in general. Might be biased. The other thing is that there's sort of a perspective shift in that the overall big difference between these two theorems, or like these two algebraic structures perhaps, is here we're building like the Witt vector restriction into our pro system, and so that's part of the inherent structure. And we add additional Frobenius and Verschiebung operators. Here, we're building the Frobenius and Verschiebung operators into the basic structure because they're part of this being the data of a Mackey functor here. And then some extra stuff, the extra stuff will have to include the analogous of the Witt restriction. So we sort of like swapped which bit was part of the structure and which bit was additional properties. And of course, like, Helmholtz and Maxim were defining things in the way that they were because they were interested in understanding some of the connections to non-equivariant algebra more than the connections to equivariant algebra at the time. That was the connections they were looking for. So what I'm going to do next is tell you about many of the ingredients in this equivariant theory. But if there are any questions, happy to take them. Okay, so first ingredient I'm going to talk about briefly is twisted THH. So how does twisted THH work? We start with a CN ring spectrum. So, for example, in the case we care about, we're going to take A to be an Riemann spectrum of our Mackey function or our temporal function R. And then, easy way to describe what twisted THH of A is that, well, it should be the norm from S1 to S1 from Cn of the ring spectrum A. So again, let me say that this is all work of Engelweit, Blumberg, Gerhardt, Hill, Wilson, and Mendel. But, maybe let's be a little more concrete about what does this mean. I mean, this is supposed to tell you some sort of left adjoint, but we can actually define this as, say, the geometric realization of twisted cyclic nerve twisted cyclic complex, let's say. And what does it look like? Well, our complex looks like maybe have like 3 copies of A smashed together. That's what's mapped onto 2 copies of A and 1 copy of A. Have a bunch of space maps and then degeneracy maps, which I won't draw. And the key thing is, so, if this was just like a cyclic bar construction, I would have multiply here, wrap this one around and multiply. Those would be my face maps. But now I'm going to have to incorporate the CN action into the last face map. So my face maps look like, they're like x0, enter x1, enter x2, goes to x0 times x1, enter x2, or to x0, enter x1, enter x2, or the last one is I take g times x2. Here, g is the generator of n, and then times x0 into x1. So this is like 0, 1, 2. These are my face maps. And then I take the geometric realization of this complex. And what do I have? I should think that this is basically like the complex I would have twisted, a cyclic complex I would use to define something like THH, except that now I've inherently twisted in the pre-existing CN action into the structure I have. Okay, and so what does this bind me? This is not really a cyclic object anymore. This is the lambda CN. We already down here. This is a lambda CN guy. Object, which is kind of like a cyclic object, but with this twisting of CN in. And so its geometric realization has an S1 action. And Engelbeit, Blumberg, Gerhardt, Lawson, and Mandel show that this construction gives you something that deserves to be called this norm. It satisfies the appropriate adjunctions that give you a norm. And it's very nice. It has properties that we would like to have. In particular, when n is prime to p, the same authors show that THH of A is p atomic, and so in particular we get maps of the following form. So if I take THHCN of A, the twisted THH, I can take its fixed points under CP, because it's an S1 gathered, and then maybe take further fixed points under CP to the K minus 1. Overall, I've taken CP to the K's worth of fixed points. The CP fixed points map to the CP geometry, always. And then the cyclotomicity gives me a map from the geometric fixed points back to the THH. So I have maps like this that compare. What are we ultimately comparing? This is comparing the CP to the K fixed points to the CP to the K minus 1 fixed point, which I could compare just by inclusion of fixed points, but this is another funny way to do it. That's an important piece of the cyclotomicity.
Is there CN in red maps? Is everything else CN?
The S1 S so it's also. Yeah, I'm being sloppy. I should be careful about S1 and reinflated S1 because it doesn't mean S1 mod to TH and things like that. But I'm going to brush that under many rugs. Okay, this is a very quick introduction to twisted. Now I want to tell you a little bit about our other main ingredient, which is the equivariant Witt. The the takeaway here, the takeaway from THH is really that, like, it's like THH, but I started with the CN action, and I'm keeping that CN action around. I'm sort of not forgetting about it and then like putting in a new one with my S1 action. I'm keeping that CN action around as part of my S1 action that I'm building. So what about the equivariant vectors?
Marie, did we use the combined structure in here, or the underlying commutative green function structure would give me the same thing?
No, the underlying commutative green function structure gives you the same thing. Okay. I think that's right. But it won't be. I mean, it won't be a left adjoint.
Yes,
of course. In fact, both of these ingredients don't really necessarily, but we do need it for. Okay, so the equivariant Witt vectors. So again, these are defined by Lumberg, Gerhardt, Lawson. And so, what's the context in which these exist? So these you have equivariant Witt vectors. For if I start with the green functor, I would have equivariant Witt vectors WGH or G of R underlined for R and then H green functor. And G group containing H, and maybe I want them all to live inside of S1. So again, I'm really thinking about cyclic groups here. Okay. And I drew an underline on the symbol for W because these Witt vectors are themselves a green functor. So a green functor of Witt vectors. Green functor I created. One way to define them is I can say that Witt vectors, equivariant Witt vectors for R are defined to be equivariant optional homology with respect to G of the norm from G to H. So this is like a zero, this is the zeroth like twisted Hochschild homology of this green functor that I get by norming R up to H, up to G from H. Might not be that satisfactory. So I will tell you another way to think about them. But one thing I want to point out here, one reason I wanted to write this definition down in particular, is that this is both telling you that this is related to Hochschild complexes, which is what we're doing in THH, so it's like not crazy that they're related. And it's also, here we're seeing some additional norm structure coming up. And as I said, that's the big norm, this is going to be a theme in this talk. Okay. So, just maybe some terminology. So for there is CN being inside of T to the KN, cyclic group inside of this one, then T to the KN Witt vectors of R, my H. These are called the length plus 1 P typical Witt vectors. And why might we want to call them this? This is because when the N is a trivial group, these length K plus 1 P typical Witt vectors of what is a green functor over the trivial group is just a ring R, so I'm going to write R with no underline, just a ring here, this is supposed to be a CP to the K Mackey functor. So I will evaluate it as CP to the K mod CP to the K. And then this is the classical K length K plus 1 P typical Witt vectors of R. So I do recover the classical things out of this construction. Okay. So that's nice, like they really, I'm getting a generalization. And then I told you I'd give you maybe slightly nicer version of how to think about these Witt vectors in terms of norms. And so for our commutative, these Witt vectors are also a commutative green factor. And in fact, we have a very nice way of writing down these Witt vectors, which is that I take the norm, the CP to the Kn from Cn of R, and then I quotient by the CP to the Kn action, or I take orbits is the other way to think about what I'm doing with that quotient. So now you might be like, wait a second, I shouldn't necessarily, like this thing here, what is it? It's a CP to the Kn green functor, or Tambara functor. And like, in general, if I have a Mackey functor or a Tambara functor or something, I don't get an action of the group on it. But I do here because this is the cyclic group. And so all the Weyl groups are in fact just quotients of it. And so I can think about those actions as actually giving me an action on the whole Mackey functor and taking the quotient here. And so this is a strict quotient with respect to that CP to the K action, so this is one of many cases in which the fact that everybody is a cyclic group and then also inside of one, this is, I'm using this probably to my advantage. And
I realized I don't know what equivariant mod is.
you should read this beautiful paper of Blomberg, Gerhardt, Hill, and Lawson, and they will tell you all about it. I will not tell you all about it. But it's basically, I built something that looks like a Hochschild complex, twisted Hochschild complex, except that I do it in algebra instead of in homotopy theory. The basic idea. And then I need to make another point here, which is that all of this really is the definition in algebra. All of the pieces of this construction are really just algebra of Mackey functors and green functors, but it is a purely algebraic construction. Okay. And so, because we have the Witt vectors are connected to norms in these nice ways, we have some good identifications. So, here are some identifications we can make. So, if we have Cn fits inside of some group H, which is inside of CP to the Kn, so some intermediate group, then I can take the restriction to H of the CP to the Kn vectors of R, and this is the same as the H with vectors of R. So this just falls out of the definitions and understanding how the norms work here. And that's nice. I can also understand a little bit about, say, the geometric fixed point that's Mackey functors of the CP to the Kn. So the CP geometric fixed points of this Mackey functor can also identify them as the CP to the K minus 1 with vectors. So I think of this as like a cyclotomicity. Maybe I should say P cyclotomicity. And so I want to point out that so these are the equivariant, we're calling them the equivariant Witt vectors. And I believe maybe one reason why you should think that's not the worst name ever, which is that I do sometimes recover the the classical Witt vectors. But maybe it's even more convincing if we talk about like the kind of structure that Witt vectors would have, and you can see that they also. And I will talk about this in particular because this kind of structure will also be the kind of structure we see on the Witt complexes, which will then influence higher homotopy. So Witt vector structure. So we could have the B is mapped. These are going to be the Mackey functor restrictions. So, for example, repeat here. If I look at these p to the kn Witt vectors of R, maybe let's evaluate at some next spot. Cp to the kn mod cp to the k. Well, then I have a restriction map, which I'm going to call F because of Witt vector unit. To cp to the k and mod cp to the k minus 1, which is a restriction in my Mackey functor. But then I want to say, aha, I can use these kind of identifications and say, well, recognize that this is really the value of a restricted Mackey functor. So this is really the same thing as restricting the cp to the k minus 1 and this Mackey functor. And evaluating at cp to the k minus 1 and cp to the k minus 1. Think of this as the value of the restricted Mackey functor. And then now I'll use my identification and say, well, this was really cp to the k minus 1 n. Witt vectors are evaluated at this same spot. So what I think you should observe here is that I'm thinking of this Mackey function restriction like that would live within one Mackey functor here. But actually, I have a whole bunch of different Witt vector Mackey functors coming from choosing different k's. And in fact, these identifications mean that I can view things like the Mackey functor restriction as actually changing which Witt vectors I'm living in, instead of just like changing which level of Mackey functor I'm living in. So I like really things are a lot more intertwined than they think in my initially. And then similarly, the Witt vector over Shibam, this is going to be like the Mackey functor transfer. And again, I can use a similar kind of trick and think about it either as like living within a single green functor Witt vectors, or I can think about it as changing what k is here in the cp to the k and cp k Mackey functors. Okay. So I have these kind of structures. And one of the like terrible, horrible things about this whole subject is that you're dealing with Mackey functors and you're dealing with Witt vectors. And both of these things have things that are called restrictions. And they're not the same, and they don't line up. And like people made choices many years ago and we're stuck. And so Witt vectors should have restriction maps. Witt restriction maps. So notice these are, I call this Mackey functor restriction because it's restriction in Mackey functor. This is the other one. These are supposed to look like this. So they go from the Witt vectors of length k. Let's say. Really come more generally, but I'm going to tell you sort of what's going on just evaluated at this level. For begin with, go from length k plus 1 to length k. And how do these work? So these are not part of the actual structure of just having a green functor or a Mackey functor. These are like additional structures that I get from the cyclotomicity. So I'm supposed to take my length k plus 1 unit vectors, and then I want to view these. I want to take this is basically taking their fixed points, this functor that I'm calling zeta sub cp. And what am I really doing here? I'm saying I can view cp to the k minus 1 and set as cp to the k and sets by the quotient map or quotient by p. And so that gives me a way of saying if I have cp to the k and Mackey functors, I can view them as cp to the k and minus k minus 1 and Mackey functors. I can just drop down. And this turns out to correspond to taking the fixed points. So you should think, if I have a cp to the k and Mackey functor, its fixed point should be a cp to the k minus 1. The p fixed point should be the cp to the k minus 1 and Mackey functor. And that's what I do. There's also the notion of geometric fixed points for Mackey functors. And so the regular fixed points map to the geometric fixed points. Like that's the job of fixed points and geometric fixed points. And then now I can use my other identification here. The k minus 1 and unit vectors of R. So and right, this isomorphism here, again, this is the thing that I about Mackey functors. So the takeaway here is that I have a lot of the, I have the algebra, kinds of algebra that I expect to see on bit vectors. They're all coming up here, but naturally in a equivariant context, an equivariant flavor. And I've done a little bit of like mind twisting and re-identifying like which bits are, which bits are coming up where, but it's really some of the same basic flavors are up here. And if you don't know any of these basic players, hopefully since you're at this lovely equivariant semester, you will at least recognize Mackey functors. You can identify them here, even if you couldn't identify them in the bit vectors.
Yeah. In this point number 2, equivariant bit vectors, do we still assume that n is prime to p in all of these constructions?
For the constructions, you don't have to, but maybe for some of these identifications, you might need to, and I'm not going to answer correctly right now, and you should ask Mike or Tina during. Like in particular, I'm worried about the cyclicity. That's really the only one I'm worried about. Okay, so there's one other piece of algebraic structure I want to identify. So my collaborators and myself identified an additional piece of algebraic structure that we get on these equivariant Witt vectors. These are the multiplicative Witt maps. There are multiplicative Witt maps. And what do they use? So I'm going to call it bracket K. It goes from R evaluated at some spots. Remember, R is a Cn Mackey functor, so this is really just any spot in R. And it's going to go to the Cp to the K and Witt vectors on R. So this is, our length K plus 1 P typical Witt vectors on R. Evaluated at Pp to the K and Cp to the K. And why are they called multiplicative lists? Well, they're called multiplicative lists because they make the following diagram commute. So here's my list map. Okay, and then down here, I can take the map that sends some element in this ring X, it's e to the kth power, and we can view this as, you know, we can view this landing in R, but then I can actually view R as sitting inside of just the Cn R, Cn, Cm, and there's a general restriction map coming from the unit of the restriction co-induction junction on Mackey functors that makes this diagram. So we think of this as the lift of the p to the kth power map. That's why it's called the multiplicative lift. And I should mention that if you're very familiar with bit vectors, you might be like, wait a second, I'm off by one in my gradient convention, and I should call this is what would be called typically in the bit vector literature, brackets k plus 1. But it's like a disaster to do that in the equivariant context because it really comes from Cp to the k, and so you just shift it. Okay, and maybe just as a proposition, let me say that, you know, when R is a commutative ring, and Cn equals E, then this gives me to define these multiplicative lifts. So, and how do they work? I can actually write down exactly how you get this guy. And it's fun, and again, it goes back to my theme of you should take care of all multiplicativity by norm maps whenever possible. So how does it work? We define bracket K as the composite. So I take my Tamara function R. So here I really need Tamara. So I can map from here, and then I can map this. I can use the unit of the norm restriction adjunction and map this to the norm from Cn to Cp to the Kn of R, evaluated at the same spot. So this is the unit map of this adjunction. And then I can say, but restrictions of the Mackey functors, I know how to define their values. This is really just isomorphic, like as a ring. This norm evaluated at Cp to the Kn mod Cn. Because all I did is when I want to find the value of the restricted Mackey functor, I should just reduce this one. Reduce this guy up, and I did this. So I did that. And now, here's where I really knew that I had a power functor, is that I have an internal norm. And where does this take me? This takes me to this normed Mackey functor, but now evaluated at Cp to the Kn mod Cp to the Kn. So that's where I go with my internal norm. I'm norming from Cm to Cp to the K. As many p power norms as I can do. And then this guy maps via the quotient map that is maybe on the board. This one right here, and identifying the bit vectors as the quotient. This maps down to the bit vectors. here's, map 2 for quotient. So this is what my multiplicative would told you. And we can see again here, we're using norm structures, we're using the structure of norms to encode our powers and our multiplication. So that's what we're doing. All right, so there's a lot of structure, and now I'm going to tell you about more structure because now I'm going to give you a definition of the equivariant Witt complex, which is supposed to be encoding what happens on this. More questions? So equivariant Witt complexes. Okay, so here's the definition. And I spent a lot of time talking about the structure of the equivariant Witt vectors themselves because a lot of the same shape of structure will come back to us. It won't be exactly the same, but we'll see a lot of the same kinds of shapes. So again, you want P to be an odd prime, you want P to be an odd prime, not divided n, and then R will be a Cn, not a bar functor for sure. And again, I need the values of R to be V localized P algebra. Cn sitting inside of Cn. Okay, so then a Cn equivariant Witt complex over R is the following data. So one, I want a collection of graded green functors. We look at a collection of graded green functors. E to the Cp to the Kn is the Cp to the Kn green functor. And maybe I put an S here. I'm not changing what's going on in my notes, just for psychology. So this is a collection of graded green functors. Okay. And but they have to be related between each other. So that if I restrict like the Cp to the S1 down to Cp to the K, this one is isomorphic, compatible way with the Cp to the K one. So what I really want to think here is that essentially this family of green functors, I really actually only have one value that's coming up for every group of the form Cp to the K n. As K varies, sometimes I would be recording lots of extra data because Cp to the Kn sits inside of Cp to the Sn, but I insist that it not be extra. That they match up. And I just want to point out that since these are green functors, they come with restriction maps and transfer maps for Raggy functors, and those are going to be, again, like my Frobenius and Shiba right at here. So I've got all these green functors. And for any subgroup of Cp to the Sn, now I'm going to want to have differentials. So I have a differential on the value of this green functor at H of these values is going to be a differential graded rate, as you know, as a star variable. And these are going to be constructors preserved under isomorphisms in one. And you might think, well, this is kind of a funny structure that I'm not saying I have differentially graded green functors, but that's because I can't. It turns out that the relations that I'm going to tell you hold in terms of how transfer and restriction interact with the differential, even the differential does not, for example, commute with restriction, and so I absolutely do not have differential graded green functors. It's just not the way the world works. At least this world, in this particular small portion of it. Okay, so that's how that goes. And then there's going to be some relation. So the next bit of data that I to my definition are maps. Orange that are like my Witt vector restriction map from this sort of fixed point of the CP to the S and green functor. This to P to the X minus 1 and green functors. They're maps of green functors. This is graded. Green functors. So these maps do commute with like restriction and transfer. And 4, I should have maps lambda from the equivariant Witt of S part into the appropriate graded green functor that I have. These are maps green functors. So those also commute with restriction and transfer. So I have these kind of maps. I should think about what's going on here. I should think about in my collection of graded green functors, I have sort of Frobenius Rashimoni things. I have a differential. These maps are like Witt restrictions, and these are the maps that tell me I should have something that has anything to do with Witt vectors or Witt anything at all. Right? I have a bunch of green functors. That's how that goes. And we should satisfy some relations. The first couple are not. The first relation is that lambda and r should play nice, so r and lambda should commute, and the differential should commute with r. Second relation tells me that here I'm writing F for Frobenius and V for Rashimoni, and this should, if I do Rashimoni and the differential and then F, Frobenius, I should get the differential back. So that's like transfer differential restriction should be back to my differential. And then I should have relations that look kind of like FV equals P. Here maybe I'm thinking about the Frobenius, which is maximum functor restriction. The Rashimoni maximum transfer. And maybe the thing I should find out is I want to P here and I want to index P transfer restriction. So that's and these kind of relations these are the ones that tell us that the differentials will not commute with the maximum functor structure on a whole bunch of different things. And then we have a fun crazy relation. So what does this look like? So I do again here I'm looking at index P, Frobenius and Rashimoni, aka restriction and transfer. And if I do F on D of my multiplicative list or something, So what am I doing? I'm taking something just in R at some level, and I'm doing my R, and I'm doing my multiplicative lift, so now I'm in the mid vectors on R. I can lambda it over, now I'm in the and then I do a differential, and then I do this prediction. This is going to be equal to lambda of the lift one less time, multiplicative lift, but one shorter, and then take it to the p minus 1 power, and then do differential lambda. This is sort of something about, like, it's kind of trying to tell you that if I take d on a p power, it's kind of like d to the p minus 1 thing, like p minus 1 power times d of the thing, but in like crazy multiplicative with the vector rotation. It's kind of what it's telling you. So this is okay, and there's a classical relation in Witt complexes that look basically exactly like this. And I'm basically out of time, but remind you that the theorem is that this structure is the structure that occurs on the homotopy groups of twisted THH. And the only thing I want to say about where does it come from, maybe I'll say a little bit. So homotopy groups of twisted THH are automatically giving me a bunch of graded beam functors because I'm taking the equivariant homotopy groups. The differential here comes from the fact that I had an S1 action. So whenever I have an S1 action on the spectrum, I'm always going to get differentials like this. These maps, cyclicity, this map, Blumberg, Gerhardt, Hill, and Lawson identify what happens on side 0 of THH, and they show you to get about it. Most of these relations are fine. This relationship is beastly and requires a lot of fussing around with norms and some clever ways of sort of turning things from algebra into spectral lambs, which you can actually get between algebraic definitions of the multiplicative list and something that you can do with in spectrum. Well done.
Few questions? Well, a comment and a question. So I guess the word, it hasn't been mentioned through all these weeks. That's one of the word Mackie functor, I think, is due to Jess. Although
Yes.
the word green functor is due to green, and the green called it to G functor, I think.
It's a bar called TNR.
And, I think the cyclic bar construction is due to homotopy.
That's probably true.
Bergström and Madsen, their terminology about restriction and Frobenius was compatible with the Mackie functor terminology.
Yeah, it was like phi and something else.
Yeah, they had phi for the restriction, but they called the Frobenius, they called it restriction. So I know who introduced the conflict, but I'm not going to say.
Now you have to
Now
say
my
it.
real question is about polygonic spectra. So the description in terms of cyclic bar construct about twisted THH it only involves twisting sort of once by the generator of the group. But so it is kind of a THH with twisted coefficients, and I guess there's this notion of polygonic spectra, which says well, as is part of a structure. But there the key structure map would land not in the singly twisted, but in the people twisted. So the one where you form THH, twisted THH, where the group where you're twisting by the p power of the group action instead of the first power.
Mm-hmm.
So I guess maybe this is a question to the six authors. I mean, so why is it really p-cyclotomic? Because it looks like this, as part of the polygonic structure, it looks like it should land the 5p should land in the people twisted rather than the singly twisted THH. I mean, this may be because p is prime to n, so you can somehow untwist, but we don't quite see where that comes.
I'm not not sure, that would be, I mean, that would be my guess for the special happening here, but again, the actual piece is relatively time to end. And the six authors do only prove this piece of ethnicity in the case where he is provided for him.
I mean, I guess it would make sense that, I mean, if you were acting by CP infinity, the P power roots of unity,
Yeah,
then there would be a group automorphism that you could modify things by so that
yeah,
what access n in one case access, I mean, you could extract the entry, but if you actually wanted to be through a circle action, which you probably want in order to get the differential,
yeah,
then the nth power map on the circle is not quite invertible. So it's not quite obvious how to. But it wasn't really a question about.
yeah,
But it just seemed to me that this sort of polygon spectra is sort of one
I
way
agree,
to,
it's definitely related.
but that seems to then look at a slightly broader class of objects, namely where you're twisting not just by the single twist, but all integer twists or something.
Mhm.
So you highlighted this new multiplicative Witt structure. Non-equivariantly, if I look at a perfect FP algebra, the Witt vectors are a little bit easier to define, and in fact, there's a theorem that they're the completion of the group ring. So that in some sense, the group ring being the universal thing that has multiplicative lifts. So you take the free thing with multiplicative lifts and complete it. I was just wondering if there's a class of perfect algebras or something where these equivariant Witt vectors can be described as a completion of the universal thing with multiplicative lifts.
I don't know, that's a really good question. Yeah.
I did have a question, yeah. So it's a very complicated structure you described. What is the state of calculation at the moment? You know, I mean, are there examples of this that have been?
I think the answer is not in detail. But if you want to do one, that would be.
No, I mean,
In the case where the group is trivial group, these calculations are somewhat
Yeah.
elaborate. Right, well, let's hang on here again.